When sigma or population standard deviation is missing, we need a new distribution. If the distribution of a random variable like x is approximately normal, then this new variable t, which is defined as x bar minus mu divided by s over square root of n, follows a distribution that we call t distribution or student's t distribution. The critical values of t are denoted by t sub c, which are different from z sub c. So if sigma or population standard deviation is given, we're going to use ZC, but if it's missing, you're going to use sample standard deviation, and then you're going to calculate T sub C. There are important properties for this distribution. First of all, the mean, median, and mode of T distribution are all equal to 0, similar to standard normal distribution. The T distribution is bell-shaped and symmetric about the mean. The total area under the T distribution curve is equal to 1 or 100%. The tails in the T distribution are thicker than those in the standard normal distribution. Also, the standard deviation of the T distribution changes with the sample size, but it is greater than 1, everyone. The T distribution is a family of curves. Each one is determined by a parameter called the degrees of freedom. The degrees of freedom, sometimes abbreviated as DF, are the number of free choices left after a sample statistic such as X bar is calculated. When you use a T distribution to estimate a population mean, the degrees of freedom are equal to 1 less than the sample size. So the degrees of freedom is n minus 1. The visualization for a T distribution is like this. If the degrees of freedom is equal to 2, then the graph very similar to a normal curve, but as you can see, you have a larger distance between the tail of the curve and t-axis. However, when the degrees of freedom increases, the graph is getting closer and closer to a normal distribution, or more precisely, standard normal curve. As the degrees of freedom increase, the T distribution approaches the standard normal distribution as shown in the figure. After 30 degrees of freedom, the T distribution is close to the standard normal distribution. Very well. You can use a table or a software or a calculator to calculate the critical value T sub C. So on the very first row, you have the level of confidence C. 80%, 90%, 95%, 98%, 99%. The degrees of freedom, they are all located on the very first column. To find the critical value, you need to find an intersection between this column and the given level of confidence. So if the level of confidence is 95% and the degrees of freedom is 11, then you need to find the intersection between 11 and 95%, which is going to be this number here. So that's how we find the critical value for T distribution using a table. For example, you randomly select 16 coffee shops and measure the temperature of the coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold and assume that the temperature are approximately normally distributed. Please note that we don't have the population standard deviation. We only have the sample standard deviation. So we have to use T, not Z. We need to calculate the critical value TC, not ZC. Z is not correct because we don't have information about population standard deviation. Because sigma is not given to us, the sample is random and the temperatures are approximately normal, we're going to use T distribution. The collection has 16 temperatures in it. The average of the temperature X bar is 162 degrees. S, or sample standard deviation, is 10 degrees, and confidence level is 95%. The degrees of freedom, which is 16 minus 1, is 15. So take a look. You have 95% level of confidence. Degrees of freedom is 15, which is just right here. Now, if you check the intersection between this row and this column, you can easily find the critical value 2.131. As you can see, the critical value T sub C is 2.131. Why it is important? Because it helps us to calculate E, or the margin of error. Margin of error is TCS divided by square root of n, which is 2.131, what you calculated from the table or your software, times 10. 10 is the sample standard deviation divided by square root of 16, which is about 5.3 degrees. The left endpoint is X bar, or the average temperature, minus the margin of error that you found here, 162 minus 5.3, which is 156.7, and X bar plus A is about 162 plus 5.3, or 167.3 degrees. So you can say that, hey, the population mean temperature is bounded between 156.7 degrees and 167.3 degrees. Are we 100% confident about that? Of course not. With 95% confidence, you can say that the population mean temperature of coffee sold is between 156.7 degrees and 167.3 degrees. So again, the important key is you have a sample standard deviation. That's why you're using T distribution. If population standard deviation is given, you're going to use Z. That's the main difference between these two distributions.